Alright, welcome. I'm glad to be bringing you this video on Buffer Overflow exploits. This is a custom overflow exploit based around the CloudMe software. CloudMe is kind of like Dropbox or OneDrive. It lets you upload your files to the cloud and then keep them in sync across multiple computers. So we're going to break it. Let's first understand what a Buffer Overflow exploit is. So imagine that we have the CloudMe software open and we have a username variable that stores your username in the actual code of the software. And say it only holds 5 characters. I type in Nate, no problem, it's only 4 characters. But say I type in way more than 4 characters. Well, how does the program handle it? Sometimes it doesn't. Sometimes what happens is that the software overflows. And that means that the username variable can't hold all the data, and so that data overflows into other parts of the software. The result is the different registers in the CPU for the memory of that software are overfilled with a bunch of extra data. The idea is that we can change this extra data to overwrite the correct registers in the CPU to tell the program what to do. And so essentially we're going to hijack the program flow to do what we want. We're going to point it towards some malicious code that we have. So this is basically how registers are set up. You can see a bunch of different registers. They all have different purposes, and most of them are basically for doing math. The important register that we're paying attention to right here is this one, EIP, or the instruction pointer. The EIP register holds the destination of the next address in memory that the program is going to access. And so we want to overwrite that address in memory with the address of some malicious code that we're going to inject into our software. So let's get started. The first thing we're going to do is open up Immunity Debugger. And before I start, let me tell you what I have. I've got Immunity Debugger. I've got Python 2.71. I've got CloudMe version 1.71. And then I've got Kali Linux running right here in VirtualBox. And so Kali Linux is going to give us access to some penetration testing tools. A lot of people think it's for, script kiddies, but Kali Linux is an incredibly stable operating system with a bunch of tools just ready for use. So we're going to throw it up in VirtualBox and use it for creating this exploit. So first off, let's take a look at the actual vulnerable software real quick. We're going to use a handy little tool called Get-PESecurity, right? So Get-PESecurity, they got a GitHub entry right here, and it's a PowerShell module that checks if Windows binary has been compiled with ALSR, DEP, SafeSEH, or any of these things. And so essentially what ALSR, DEP, and SafeSEH are protections against buffer overflow exploits. So in a lot of Windows machines, and really every operating system, software is compiled with buffer overflow exploits in mind. So we want to make sure that it's not been compiled with any of these built-in protections. All right, so what we're going to do is we're going to download the PESecurity files, the little PowerShell script. And I've already done this, so what I'm going to do is I'm going to open up the location where I downloaded it. I'm going to throw it up in PowerShell. And I'm going to import the module. So it tells you right here exactly how to run PESecurity. You basically go into the directory that it's at, and then you import the module. So this imports into PowerShell and lets you use it. We're going to run it. And then we're going to say get PESecurity, and the file we're going to give it is the CloudMe file, the CloudMe executable file that we're actually trying to hack into. So we're going to give it the location, and we're going to say cloudme.exe, and we're going to put this in quotes just because program files has a space in it, so we want it to know that it's a string literal. All right, so ALSR is off, DEP is off, SafeSEH is off. When it says false, that means it's off. So that means we're ready to go, we're ready to start testing our exploit. So the first thing I'm going to do is open up this software in Immunity Debugger. And what we're going to start by doing is we're going to start by fuzzing the software. Now you can download a bunch of software to help you fuzz manually, that can help you fuzz in an automated way. But we're going to fuzz it manually because I think it's really important to understand what the fuzzing process is actually doing. So we're going to create a little Python software. We're going to call it overflow.py. I'm going to save it in the documents. And we're going to do a few things. First, we're going to give it an IP address to access. Now, keep in mind, CloudMe is running on a specific port on your computer. And in this case, CloudMe is actually running on port 8888, right? So we can run netstat, and we can search port 88888 with FindString. And we can see that it's running on port 88888. It's open, it's ready to go, it's ready to attack, right? So we're going to give it the port 88888, and then we're going to create a socket, right? We're going to call it sock, and we're going to say socket, right? And then we're going to say socket.afinet socket.sockstream. Right, and so basically what this does is it creates a socket, which is essentially a direct connection to that port, to that IP and that port. And then what we're going to do is we're going to say connect to IP and port. I'm going to tell the socket to connect to IP and port, and then we're going to tell the socket to send an exploit. Right? And right now, we don't have an exploit yet, so we haven't built it, so we're going to leave it blank. But we're just going to test. We're going to execute it, and we're going to make sure that it's able to connect. And then at the end, we're going to say sent the exploit. So basically, if it doesn't crash, you know you've done something correct. You know you're ready to go. So we have this open in Immunity Debugger, and Immunity is going to let us break down this software and understand how it runs and where it's crashing. But first, we got to crash it. We do this through fuzzing, right? So the idea is that you take a single character and you send it to the software. Obviously, the buffer can hold a single character. There's no issue with that, right? It doesn't crash. You can see here, everything's fine. We've got no problems. But what if we send more than one character, right? What if we send a bunch of characters? So we're going to test this out. The first thing we're going to do is disable our antivirus because that's extremely important. If you have your antivirus enabled, it can actually block some of these exploits, or it can remove the exploit code from your system. So right now we're going to try sending 200 ends. And we're going to see if it crashes. Okay, 200, no crash. What about 500? No crash. Awesome. So our application is maybe a little bit resilient. It won't crash with 500 characters. At least it's got a 500 character buffer. We're going to try 1,000 characters and see if it crashes. All right, it doesn't crash. Now we're going to try 2,000 characters and see if that does anything. And this is essentially what a fuzzing program would do automatically, right? And I don't know if you noticed that there, but it looks like CloudMe just closed up. So let's open it back up and let's try this exploit one more time and see if it's actually working in Immunity Debugger. We're going to see if it actually crashes it through Immunity. When you first open Immunity up, it's just going to give you an overview of the software, and you got to click this little button right here for play to actually open up the software in Immunity. So we got it open in Immunity. We're going to send that exploit one more time, 2,000 characters, and we're going to see if 2,000 characters actually crashes the software. All right, so Immunity Debugger kept the software from automatically closing. It's frozen, but we can see right here our ends overflowed and filled up a bunch of registers. We know it's an N because N in hex is 4E. So take ASCII, right, an N in ASCII, and you convert it to hex and you get 4E. So we see 4E on all these registers, and that's great because we see that the EIP register, remember the instruction pointer register that we were talking about, that register has been overwritten, right? That's key for us because now that we know that we've overwritten the instruction pointer register, we know that we can overwrite it with custom code, and that's what we're about to do. All right, so I've enabled a little bit of transparency so that you can see the software running behind it, so we can see when it closes. We can kind of understand what's going on here. All right, so we see that the EIP register is overwritten, so what we're going to try to do is figure out exactly where the EIP register is. We need to know the offset. We need to know how many ends that we send before we actually hit the EIP register so that we can overwrite the EIP register with the custom value, right? And this is where Kali comes in. So we're going to open up Kali. Let me make it a little smaller here. We're going to open up Kali and we're going to use a handy little program included in the Metasploit Framework, and it's called Pattern Create. Pattern Create and Pattern Offset, right? So what Pattern Create does is it creates a pattern. We're going to search for pattern offset command. So user share Metasploit Framework, tools, exploit, pattern create -L and 3000. And so what this is basically going to do is it's going to create a 3000 character pattern. And with that pattern, once we enter that pattern in, we can take whatever value hits the EIP register, put it into our pattern offset code, and it'll tell us what the offset of the EIP register is. So, go. Let's see, what are we doing wrong here? User share Metasploit Framework, tools, exploit pattern create.rb. That's the name of it. So it's a Ruby file. So it should create a 3000 character payload, and instead of the ends, we're actually going to replace the exploit with this custom 3000 character payload that it gives us. So we're going to copy this whole thing, throw it in here, and then we're going to do the same thing that we did before, except we're going to rerun this. So we click this little back button and it'll rerun the software. It'll open it up again so that we don't have to use the old frozen version. All right? So we run it back, then we press play, and it should open up CloudMe one more time. And then we're going to inject this pattern right here, and you're going to see part of that pattern show up in the EIP register. Let's check it out. All right, boom. So the EIP register has this pattern right here, 694235, etc., right? So we take that, we bring it into our Metasploit window. Let's see if we can scale a little better. We bring it into here, and we change it from pattern create to pattern offset, right? And then instead of just L3000, we also say Q, and we give the little number that was in the EIP register. So this is going to give the offset to this part of the area, right? So we know that the offset is 1036, right? We're going to test that, right? We're going to go back to this exploit, and we're going to say fill it up with ends until we get to 1036, and then fill it up with some B's, right? So we're going to run this back, and we're going to run it one more time. All right, CloudMe's open, so we're going to run this real quick and see what happens. All right, so we sent the exploit, and boom. We got 4 E's in the other registers, but the EIP register we wanted to rewrite, look at that, all B's. Translate B from ASCII to hex one more time, and B equals 42. So we know we can successfully rewrite the EIP register. So our next goal is to search this software so that we can find a proper instruction to redirect the program flow, right? So how are we going to redirect the program flow? I'm going to tell you. We're going to use an instruction that's already in the code. We're going to use a jump command, which is an opcode that allows you to jump from one instruction to another, to jump from where we are, jump our EIP from where we are to our malicious shellcode that we're going to add in here later, right? So we're going to use something called Mona, right? It's a Python library. I think it's developed by Corellan, and it basically works as a plugin for Immunity. You can run Mona commands, and so what we're going to do is run Mona, and then we're going to say JMP jump and then RESP. And so what this is going to do, it's going to take a minute, but it's going to search, right, until it finds all the jump commands in our software. So remember, Immunity might be a little slow, but it's only because it's searching through thousands of lines of code to get you what you want. So we're going to give it just a second to load up. While we wait for it to load up, we're going to work a little bit more on this exploit. We're going to get it ready, right? So we got an exploit buffer right here. And we're going to start by filling it up with a bunch of ends until we get to the EIP register. So we're going to say get to EIP. And then we're going to add to the exploit. We're going to add some more information to it. After it gets to the EIP register, we want it to jump. Okay, we want it to jump. But to get it to jump, we have to give it the address of the jump command that we're trying to use, right? So the way that we give it addresses is like this, okay? Struct.pack, L, and then the address, 0x0000 or whatever the address is. The reason we use struct.pack is because the processor works with little endian architecture. And so the translation of that is basically, if we have an address that goes 0x123456, what we need to do to actually pass it is reverse it. And so it would be 654321. We don't want to do all that. We just want the pure address of the register. And so this will automatically reverse it for us when it sends it. So that's what we're doing there. And then we're going to make room for our shellcode. This is going to be where we have all our shellcode that actually tells it the malicious instruction to execute. All right, so we're back. So this finished searching, and so what we found was we found a bunch of jump instructions, and we're going to choose one to use, right? Let me take this off so I don't get hit with a copyright. So we see a bunch of different jump instructions, and what we're looking for is a jump instruction in a file with no protections enabled, no ALSR, no SafeSEH, no dep, nothing like that, right? And we also want something with no return value because that can offset a little bit. So right here we see a jump command, right, in qtcore.dll, qt5core.dll with no ASLR, no SafeSEH, no protections at all. And so this is a DLL file that contains instructions that we're going to leverage to do what we want, to jump to where we want, right? So we're going to copy this line, and we're going to throw this in here, right here as a comment so that we know exactly where we're pulling from, where we're pulling information from. So we're pulling it from this address right here, 0x688DD4ED, right? So that's what that's the address we're going to do, and it's a jump ESP command, and this is the information on it, right? So now we have our jump, and the last thing that we need is our shellcode. There's two ways to do this. There's a few ways to do this. You can look online for existing shellcode to use, which I've already looked up some shellcode for opening a calculator, right? I'm talking about calc.exe. On Windows, it's the native calculator. I just want to open up this calculator so I can show that it's actually allowing me to execute any code that I want. I could replace that code for the calculator with a reverse shell. I could, replace it with a piece of malware, really whatever. But I don't want to go into all that now. What I really just want to do is test that the exploit works, test that I can create a calculator. And so essentially, if this was on someone else's computer, they'd be using CloudMe, and all of a sudden, I'd send my exploit, and boom, a calculator would open up, a virus would open up, a worm would open up, whatever it is. Now I have command execution on their system remotely. So we're going to copy this shellcode real quick and see if it works. We're going to add our shellcode in. Copy all of this. All right. So we have our payload, we have our exploit, we've got every part of it. We got the offset to the EIP, we've got the jump, and then we've got the shellcode. So we're going to run this real quick, and we're going to see if it works. So we're going to run CloudMe real quick, and we're going to go back to the main thread to see if it actually does what we want it to. All right. So we close this down and then we execute the code. Remember, keep your antivirus turned off. It's very important. So we see that it freezes, but we don't see much else. It pauses, it freezes. What else do we have? We see that there's an error at some point, but that's about all we see. Gonna make sure that our antivirus is completely off. I'm going to run this one more time. And what we're going to do is we're actually going to close out of the debugger and just run this software so it's connecting directly so that the debugger doesn't hold it up at all. And we're going to throw this in here. All right, look at that. So it sent the exploit. It crashed the software, right? So the software closed, but it also opened up Calculator. So at this point, what I could do instead of Calculator is I could have it open up a virus or remote shell to my computer. The software would crash. Someone would think, oh, it's just, you know, a buggy program, but really I've got a reverse shell on their computer. I've got remote access. So there you go. There's more instructions on how to do this, some guides that will help you, as well as the download for this software and, you know, all the rest of the software that I'm using and the commands in the description below. I'm going to be making more cybersecurity videos coming up here, so like, comment, subscribe. You know the drill, y'all.